This is section 7 of the ACT Math Manual, Proportions. This starts on page 51. As it says, proportions are tested in a couple of different ways on the ACT. We're going to go through most of them in this section. Now, almost all students, by the time they get to their junior and senior years, they understand how to set up and solve a direct proportion, and they have some understanding of what's going on when they are doing so, but there are going to be some questions on the ACT where it possibly might benefit you to have a little bit of a deeper understanding or more thorough understanding of what exactly a direct proportion or variation is, which is what we're going to talk about right now. So in a direct proportion or variation, most students are abundantly familiar with these two guys on the left. These are, this one fraction equals another fraction. These tend to be the most common types of proportions on these standardized tests, but these other four representations of a direct proportion or variation may come in handy on certain questions. Now, the three statements here, these are all just different ways of describing a direct proportion or variation. The first one is most analogous to the two things I just highlighted in yellow here on the left. The ratio of two quantities is constant. That constant that the ratios are equal to is called the constant of proportionality. And actually in this third representation, we can see we've inserted the constant of proportionality between the two ratios, between the two fractions. Remember that when we set up proportions, we generally leave out that constant of proportionality because we know that if A equals B and B equals C, then A equals C. In other words, if we know that our first ratio equals the constant of proportionality and our second ratio equals the constant of proportionality, then this first ratio and this last ratio, they have to be equal to each other. Again, A equals C. And that is why we generally write proportions like this second example here, where we just set the two ratios or fractions equal to each other. Now, an extension of that, or I should say, again, just a different way of writing that, is that when we have two quantities whose ratio is constant, that ratio obviously equals a constant. So if I say that there are two boys for every three girls, and I say that is a constant ratio throughout, let's say, all classes at a certain school, and then I say there is a class that has 20 boys, well, this ratio is obviously equal to 2/3. That would be my proportionality constant. If I then say that a class has 20 boys and I wanted to know how many girls there were, I would set 20 over G, 20 over the number of girls, equal to that proportionality constant, and then solve for G by cross multiplying. So again, every time you see a question that establishes that two quantities are related directly or related in a direct proportion or variation, you have to understand that what ACT is doing is setting up a proportionality constant, a K, for you. Now, statement number two is actually sort of like this fifth guy here, y equals kx. One quantity is found by multiplying the other quantity by a certain constant. So for instance, check this out. If I were to solve this, I would get 2g equals 60, and then divide by 2, not g, divide by 2, and I get g equals 30. Well, look at how this 20 and this 30 relate. Notice that in order to get the 30, I would multiply, I'm running out of room here, let me slide over here. So 20 times, I'm going to say 20 times some number, and hey, I'm going to use a k, is going to equal 30. So if I divide by 20, I get k equals 3/2. So the proportionality constant here, if I want to go from girls, so the proportionality constant here, if I want to go from boys to girls, I have to multiply the number of boys by 3 halves in order to get the number of girls. And that relationship will always be true. If I want to go from boys to girls, I always have to multiply by 3 halves. If I want to go in the other direction, girls to boys, I always have to multiply by the reciprocal, by 2/3. So again, one quantity is always determined by multiplying the other quantity by the constant of proportionality, or its reciprocal, obviously, depending upon which way you're going. Now, this third way, when one quantity is multiplied by a certain factor, the other is multiplied by the same factor, well, we can use this example to illustrate that as well. I went from 2 boys to 20 boys, so I have multiplied my boys by a factor of 10, which means I have to do the same to my girls, which is exactly why I ended up with this 30 here. Look, I know that was a lot of information to throw out right at the beginning. Like I said, it is going to be important on certain questions that you understand or are able to think about direct proportions and variations in a few different ways if you're going to want to be as confident as possible on proportion questions. So let's talk first about some of the tip-off clues, some of the things that we can look for that will tell us that ACT is testing us on proportions. The first is really silly and obvious, and that is if the question just comes right out and says directly proportional. Or they could also say, so directly proportional or varies, that's not a V, just so you know, that's a W. We could also say varies directly. Varies directly. So if ACT just comes right out and says one of those two things, you know you're dealing with a direct proportion or variation. Another phrase that you could look for is at this rate. Another type of question that almost always will involve setting up a proportion will be scale questions. So if they say, somebody's building a scale model, or somebody is making a map, and the map is 1 inch to 10 miles scale. Anytime you see the word scale, you're probably going to be setting up a proportion. You're almost definitely going to be setting up a proportion. And then the last one is the least obvious. This is a pair of items or units repeated. So if I see a pair of items or units repeated, and I'm going to jump down here to number 6. I'm not going to do the question right now. I'm just going to use this as an example of what I mean. So notice here we have, this question actually does just come right out and say directly proportional. So that's the most obvious tip-off clue. So we probably could just stop there. But notice it also has pounds and pounds. So there's one repetition of units. And then we have, in addition to the pounds, let's do the other unit in, ooh, that's a nice little lavender purple there. We also have this dollar, and then this cost or this cost. So we have cost, and unit of dollars, and then we have pounds. So anytime we see that repetition of items or units in a question, we know that we are dealing with a proportion and that we're going to have to set one up. Now, in terms of the direct proportion process here, most of you are familiar with this. I'm going to write it down so that it's solidified and so that you can always refer to this just in case you need to. So step number 1 would simply be to draw this. You just draw 2 fraction bars and an equal sign between them. And note that we are focused on these types of proportions where we've got 2 ratios that we have to set equal to each other. So we draw the fraction bars that will house the 2 ratios. We put an equal sign between them. Step number 2 is we fill in all knowns. And remember, usually there will be 3 knowns or 3 givens. Fill in all knowns or givens. Usually there will be 3 of them, and then the 4th one will be an X. You might even want to add that. Put a variable in I'm going to continue this down here. Put a variable in for the unknown or missing quantity. So again, you'll fill in 1, 2, 3, and then let's say, this guy will be missing, so we'll put in an X there. Now, really, really important when you are filling in your knowns and your unknowns and so on and so forth, you want to make sure that you write your units. So if you have got girls, 2 girls for 3 boys, similar to the example I gave you before, then over here, let's say they say we go to 10 girls and we'll do B boys. So this is what I mean by writing your units. You want to make sure that you're writing your units so that you also make sure that your numerators and denominators are matching up, that you're putting your quantities in the correct place. One of the most common careless mistakes on proportions questions is to accidentally flip one of the 2 ratios so that you are no longer relating quantities that are allowed to be related. Now for number 3, this is the solution step, or at least the beginning of the solution, and that is just cross multiply to solve. So again, you draw your fraction bars and your equal sign, you fill in everything you know, writing your units as you do, and then you cross multiply to solve. Now let's see how this would work on a fairly straightforward question like number 6 at the bottom of page 51. So price of a pumpkin is directly proportional to its weight. If a pumpkin that weighs 15 pounds costs $3.25, how much will an 11.4 pound pumpkin cost? Now we have 2 of our tip-off clues, as I said before. We have the really obvious one, which is that it comes right out and tells us that these quantities, the cost and the pounds, are directly proportional. And then we have that repetition of units, as you can see with the highlights here. So I'm just going to follow the process. The process says first, 2 fraction bars and an equal sign. Second, start filling in the knowns, including the units, so 15 pounds. And I will put the cost that corresponds to down here, $3.25. And now I know that my pounds needs to go over here in the numerator. Sorry, that needs to be 11.4 pounds. Let me get that out of there. So that needs to be 11.4 pounds in the numerator, and then my cost is my unknown, so I'll do C for cost. So now in order to solve, this just becomes a simple cross multiplication question. I am definitely going to do this in my calculator. 3.25 times 11.4, that equals 3705. So from there to there, that's 3705, and then equals 15c, divide by 15, divide by 15, go back to the calculator, divide by 15, and I get my answer, which is 247. So make sure that's what they were asking. Cost of an 11.4 pound pumpkin, 247. Yes, it is, and we are done. Again, fairly straightforward example of a proportions question. Don't think too many students are going to have too much difficulty with a question like that. Now, in page 52, unit conversions do show up every now and then on the ACT. You can do a lot of unit conversion questions with exactly the same process that we just talked about on the previous page, where you just set up 2 fractions on opposite sides of an equal sign and then cross multiply. Number 20 is a good example on which we can do so. Let's go ahead and do number 20. If you want to try it on your own, go ahead and pause the video. I'm going to go ahead and work through it right now. How many minutes would it take a train to travel 90 kilometers at a constant speed of 120 kilometers per hour. So they're looking for minutes, and notice we're given the speed in kilometers per hour. So we're going to eventually have to do some kind of a unit conversion. But on this question, probably the easiest thing to do is to do the unit conversion before we even set up the proportion. In other words, 120 kilometers per hour, 120 kilometers per hour is the same as 120 kilometers per 60 minutes. So now we have 120 kilometers. Notice I'm writing my units per 60 minutes is 90 kilometers per m minutes. Let's do m. By the way, notice we do have that repetition of items or units here. We have minutes and hours. So there's the repetition of time. And then we also have the kilometers and kilometers. So that tip-off clue would tell us, yes, we do have to set up a proportion here. So when I cross multiply, I get 120m equals 5400, and then when I divide by 120, I am gonna obviously use my calculator for that. I'm not gonna do any canceling or anything. I'm just gonna go right into my calculator and do 5400 divided by 120. Not 110 though, because that will give me something that I don't want. And then I hit enter and I get 45, and that should be my answer. I'm going to write down m equals 45, and then just make sure that's what they're asking, minutes to travel 90 kilometers. Yes, that's what we found. So our answer is H. So again, if you have a very simple conversion, you can do the conversion before you even set up the 2-ratio equation. Now, unit conversion through multiplication of linking equivalencies and unit cancellation. For those of you that took chemistry and did stoichiometry, where you had to convert things from moles to atoms or to kilograms, so you had to convert between number of atoms, moles, mass. You probably have quite a bit of experience with this. This is just a general outline or model of what this will look like. You're going to have some kind of starting unit, and then through cancellation, you will try to end up with your desired units. I don't know why that X is there. You'll try to end up with your desired unit, and obviously, if you just have one linkage, you might have something like your starting, and then you just multiply by your desired unit over your starting unit, and you would end up with your desired. Again, this is just sort of an example or a model of what a conversion might look like, and in this case, obviously, you have a two-step conversion. So on examples 1 and 2, 2 is definitely the much harder and trickier one, I should say. You can go ahead and do those on your own if you'd like. I'm going to go ahead and do them right now. So we want to get to kilograms. That's our desired unit. And our starting unit is pounds. Starting is pounds. So we're going to actually do something like this here, because we only have one step. We have kilograms and pounds. We're going to do 56 pounds. I'll abbreviate 56 pounds times. So remember, that's the starting unit. I want to be able to cancel my starting unit. So that unit pounds has to go in the denominator here so that these guys will cancel. And obviously my desired unit, which I want to be left with, will go in the numerator. And now I just fill in the numbers that I'm given. So 1 kilogram, 2.2 pounds. So I have 56 times 1 over 2.2, and in the calculator 56 times 1 over 2.2, which I could also do by 56 divided by 2.2, that would be okay as well. So we get 25.45. I'll just truncate the decimal there. No need to worry about significant figures since we're not in chemistry class. So 25.45, and obviously that would be in kilograms. That would be our final unit. Now, could you have done this just setting up a regular old fraction equals fraction proportion? Yes, you definitely could have. I just did it this way so that we got a little bit of experience with the unit conversion on an easier question before jumping into this harder one. which example 2 definitely is. What is the area this is example 2, what is the area in square feet of a rectangle 16 inches wide by 22 inches long? Now, the common mistake on a question like this is that students will multiply 16 by 22. 16 by 22. They will get 352, and that is square inches, because remember, yes, I multiplied these two numbers, but I also have to think about the fact that I'm multiplying inches by inches, which gives me a unit of inches squared. Inches squared is a unit of area, whereas inches itself is just a linear unit that just measures distance or length. So when I multiply two lengths together, I get area, and I need a unit of area. So 352 inches. Then what a lot of students do is they say, okay, so I want to convert to area in square feet. That should have been circled. So I want to do 1 foot over 12 inches, and then they will get 352 divided by 12, which equals 29.3, and they'll think, great, I am done. That is my number of square feet. This is not correct. And if you had paused the video and done it on your own and got 29.3, pay attention. You'll need to know how not to make that mistake again. So there's two ways to think about converting these inches and the area they produce to square feet. One way is to just do the linear conversion first. In other words, take the 16 inches, multiply that by 1 foot over 12 inches. So we're just doing what we did in example 1. We're using the linking units to cancel out inches and be left with feet. So 16 over 12, 16 divided by 12 is 16 divided by 12, I said, calculator. I said 16 divided by 12, calculator. So 16 divided by 12, just give me a minute while I have a conversation with my calculator. So that's 1.33 feet, and then down here we have 22 inches times 1 foot over 12 inches. Again, those guys cancel. We're going to be left with feet. So 22 divided by 12 is 1.83. So then from that point, I could actually just multiply these two values by each other, and I would get my number of square feet. So that is one valid way of doing this conversion. Just make the linear conversion from inches to feet first, and then multiply the 2 feet together to get square feet. That would be difficult to walk if you had square feet. Now, the other way of doing this is a kind of a cool way that some of you might remember from either chemistry class or math class. You can do the 16 inches by 22 inches and get that value that we got before, which was 352. This was 352 inches squared. You can actually go right from inches squared to feet squared as long as you square the conversion factor. So remember, the conversion factor was 1 foot to 12 inches. If you square this, remember what that will produce. That will produce 1 foot squared is 144 inches squared. And now you have set this up so that your inches squared here will cancel with your inches squared here. You will be left with feet squared. So if you do 352, let's do that, 352 times 1 divided by 144, I am all over the place here, 144, you get 2.44 feet. And let's just confirm, let's do 1.33 times 1.83. So this value times this value, and see what we get. And indeed, we do get 2.44. There's a little bit of rounding going on there at the end. But so 2.44 feet squared is what we were looking for here. So again, you can either do it this way on the left, or you can square your linear conversion factor to get an area conversion factor, and that way is possibly a little bit more efficient. Now 39, let's go ahead and do this. I'm gonna move this over here. If you want to do it on your own, pause the video. In a downhill ski race, Margot posted a time of 2 minutes and 24 seconds for a course 1.2 miles long. About how many miles per hour? So miles per hour did she average? So the miles we already have in the right unit. Miles. The hour we don't have. We have 2 minutes 24 seconds. So we have to convert that to hours. Obviously, we could also convert this hour to minutes, but to get some practice with the unit conversion stuff that we were just talking about, I'm going to go ahead and do this by converting this 2 minutes 24 seconds to hours. So first of all, the seconds, let's do 24 seconds times, we'll convert this to minutes. So remember, there are 60, let me get rid of that. We want seconds down here, we want minutes up here. There are 60 seconds per 1 minute, so now I can cancel my starting units and be left with my desired units. So 24 divided by 60, 24 divided by 60, that is going to equal 0.4. Okay, so then this is 0.4 minutes. 0.4 minutes, that's my final unit. So then 2 minutes and 0.4 minutes is 2.4 minutes. I multiply that by my hour conversion, which is going to be, I want minutes to cancel, so minutes will cancel. I want to be left with hours, so I do 60 minutes, 1 hour, and now I will have my number of hours. So 2.4 divided by 60, and now I have my hours. So my hours is 0.04 hours. So that's how many hours. And now to find miles per hour, average miles per hour, I just do miles per hour. I do 0.04 hours. And then my miles was 1.2. 1.2 miles per 0.04 hours is equal to how many miles per hour? 1.2 divided by 0.04 equals 30 miles per 1 hour. 30 miles per 1 hour, which is answer choice B. So that is how we would do. That's pretty fast for a skier, I guess. So yeah, that is how we do a unit conversion. Again, there's other ways, possibly even more efficient ways to do that last question. I did it in the way I did it so that you could see one more example of a unit conversion. Now, inverse proportions or variations, these are very, very rare on the ACT, so I would not worry too much about these. In fact, if you are not going for a score well north of 30, you probably don't need this information. So remember what we said from a direct proportion or variation. We said that the ratio of two items was constant. Well, and basically what that meant was that if we multiplied the numerator by a factor of 2, we had to also multiply the denominator by a factor of 2 to keep the ratio constant. But in an inverse proportion or variation, it is not the ratio that is constant, it is the product that is constant. So in an inverse proportion, if I am multiplying one thing by a factor of, let's say, 2, that means that I need to actually divide this guy by a factor of 2 in order to keep the product constant. So that you can see an example with numbers, let's use 4 and 9. Actually, let's use 4 and 8. So let's say I said that two quantities were inversely proportional. Maybe it's the number of people and the amount of hours it takes to do a certain job. Remember that generally, and ACT would have to come right out and explicitly say that these two quantities were inversely related. But generally, if you have more people, the amount of time it takes to do a job is going to decrease, which is exactly what an inverse proportion is. So where one quantity goes up, the other one goes down. So in this case, our constant is 32. We know that whatever the number of people is and whatever the number of hours is, when we multiply those two quantities, we have to get 32. So let's say two people call out sick because they're slackers. So what we have just done is we have divided the number of people by 2. Well, how many hours is it going to take to complete the same job? Well, remember, I need this over here to be 32 still. 2 times what equals 32? That's right, it's 16. So what I've done is I have actually increased the number of hours by a factor of 2. I decreased the number of people by a factor of 2. I increased the number of hours by a factor of 2. And that's exactly what happens in an inverse proportion or variation. When one goes down, the other goes up. Whatever we decrease one by, we have to increase the other by that same factor. So that's a little bit of background on indirect proportion and variations. Again, these 3 statements, just like we did for direct proportion or variation, these 3 statements are just 3 different ways of talking about an inverse proportion or variation. They all say the same thing, just in different words. So example 3, let's go ahead and do this one. If you want to try it on your own, by all means, go ahead and do so. Walking at a constant speed of W miles per hour, Albert can walk a trail in 2.5 hours. If he runs at twice his walking speed, in how many minutes could he run the trail? So this is minutes to run the trail. So remember that speed and time are inversely related to each other. As my speed goes up, does the amount of time I take to get somewhere go up? No, it goes down. So these are not directly related. When speed goes up, time does not go up as well. When speed goes up, time goes down. So speed up, time down. So that tells us that these are inversely related quantities. So what I'm going to do is I'm actually going to set up the inverse proportion that looks like this first guy up here, this AB equals CD, or this second guy here, X1, Y1 equals X2, Y2. So it's going to be speed 1 time 1 equals speed 2 time 2. The product of these two guys is constant, and it has to equal the product of these two guys. So W miles per hour times 2.5 hours, and I should actually still write my units here, so let me do that. So W miles per hour in 2.5 hours equals 2W miles per hour. Remember, they say twice the walking speed. If the walking speed is W, then twice that speed is 2W, and we need minutes here. We need, we'll do X minutes. So easiest thing to do would be to convert this 2.5 hours directly to minutes, which we can do with unit conversion. 2.5 hours, we want to cancel the hours, so 60 minutes, 1 hour, so 2.5 times 60, doing it in the calculator, 2.5 times 60, and that is going to equal 150. That's going to equal 150. So I get 150 minutes here. Sorry, this is getting a little sloppy. There's not a lot of room here. I apologize for that. So this is W times 150 equals 2WX. So this all collapses now into 150W equals 2WX. W's cancel. So I get 150 equals 2x, divide by 2, divide by 2. This is going to take the guy 75 minutes. 75 minutes. Again, I apologize, there's not a lot of room to write here. So Albert can run this trail in 75 minutes. Now, just let's step back and think a little bit more generally, maybe less mathematically, about how this just worked. Notice that we are doubling our speed, which means that we should have our time. We should cut in half our time. Double the speed means half the time. Well, remember, this 2.5 hours was 150 minutes. Half that time, indeed, is 75 minutes. So again, just stepping back and looking at that a little bit more generally, less equationally, so that you can see what's going on. Now, example 4, we have a varies inversely as the square root of b, and a equals 6 when b equals 16. What is the value of b when a equals 3? So this varies inversely. Do not get intimidated by this phrase, varies inversely, as it just means, again, that the quantity of one item times the quantity of another is constant. In other words, the product of two quantities is constant. So when they say a varies inversely as the square root of b, what they're saying is that the product a times root b is constant. That's what they are saying. So a times root b is constant. So let's take a look at this. Our first a1, let's call these our 1s, and we will call these our 2s. So a1 is 6. The square root of b would be root 16, and that product, which is constant, has to equal the product of these two guys, which equals the same constant. So we have 3 times root b. So over here, this becomes 4. This is 6 times 4, so 24 equals 3 root b. We divide by 3, divide by 3. We get root b equals 8. How do we get rid of this square root? Of course, we square both sides, and we get b equals 64. So the value of b in this case would be 64. Hopefully that all made sense. If you are struggling with this stuff, you can always talk to your tutor about it, get further clarification, possibly get some additional practice questions. Now, proportion translations. These are, if you do encounter a proportion translation question, and we'll see a bunch of examples of these in a second. If you do encounter one of these, my first piece of advice to you is do not get intimidated. These actually can be some of the easiest questions on the test, as long as you know the information on this page. I'm going to cheat a little bit, and I'm going to distill this down to something extremely simple. Again, if you want a little bit more background on why this works the way it does, you can always ask your tutor or do some research online. But basically, this is the way it works. Let me go ahead, and if you want to write this down in your manual, I would recommend doing so. So varies directly as, varies inversely as something else. So usually what you're going to see is either something varies directly as something else, or something varies inversely as something else, or a combination of these two things. They may say that one quantity varies directly as one thing and varies inversely as another thing. And the really easy way to do this is to, as the heading in the section says, is to translate. So you basically take this thing, whatever's in this position, you put it on one side of an equal sign. Varies directly, varies inversely. Remember, that requires a proportionality constant. So you'll always put the proportionality constant here. And then anything that this quantity over here varies directly as will go up in the numerator, and anything that it varies inversely as will go down in the denominator. On the first example here, so let's see how this works. So we have n is directly proportional to m. So n is directly proportional to m. So based on what I just explained, remember, we have n, we have an equal sign, we have the proportionality constant, and we have, if we did have a fraction here, it would be m and then a 1 in the denominators. We just have an m. We don't have any inverse proportion stuff, so a placeholder of 1 would just go there. So this would just boil down to n equals k m. Now, I am going to give slight bit of explanation or slight bit of relation to what we were just talking about on the previous pages. Remember that n is directly proportional to m also means that the ratio of n to m equals some constant. Well, multiplying both of these sides by m, what do I end up with? I end up with exactly what I just wrote over here. So it's no magical mystery why we get n equals km. You don't have to just take my word for it based on the translation. The equation that we just wrote over here comes directly from the definition of directly proportional. Now, example 6, p squared is inversely proportional to the product of q squared and r cubed. So remember what I said, we do a p squared, we do an equal sign, we do a proportionality constant, we do a fraction. There is no directly proportional stuff here, so there's just a 1 in the numerator and there is a q squared r cubed in the denominator because these are inversely related. The p squared and the product here are inversely related. So you could either write this as we just did, p squared equals k times 1 over q squared r squared, or you can put the k up in the numerator here since k is a k over 1, and we could just multiply these two fractions together. So I'll go ahead and write this that way. P squared equals k over q squared r cubed. So example 7 is the trickiest one of the bunch, but if you follow the rules I just said, it's not very tricky at all. So remember, a, I'm just going to go ahead and write this over here. A varies directly as, so remember we need an a, we need the equal sign, we need a constant, we need the fraction bar. Up in the numerator is the stuff that a is directly proportional to. That is the square of the sum of b and c, and in the denominator we need the stuff that it is inversely proportional to, and that is d squared. Again, I would just memorize how to do the percent translations in the way that I just told you, and if you do, questions like number 44 will be very, very simple. So let's go ahead and read this. If you want to try it on your own, which I would recommend here since we just talked about how to do these questions, pause the video and try it on your own. A person's body mass index, BMI, varies directly as, there's our direct variation, the person's weight in kilogram, and inversely as, there's our inverse variation, the square of the person's height in meters. If K represents the constant of variation, which of the following expressions represents the BMI of a person who weighs W kilograms and is H meters tall? So which of the following, following expressions represents the BMI? Okay, so that's what they're looking for. So let's actually, before we even start, let's jot down all the things we have. We have the BMI itself, we have the person's weight, which is W, and then we have the person's height, which is H, and then we have the proportionality constant. And remember what I just said. I said that we write down the first quantity, we put an equal sign, we put our proportionality constant, and then anything that this quantity is directly proportional to goes up in the numerator. Anything that it is inversely to, that it's related inversely to, goes in the denominator. So this varies directly as the person's weight. Well, remember that was the W, so that goes up here, and inversely as the square of the person's height. So it's not just the person's height, it is the square of the person's height. So the representation, the expression that represents BMI is this right here. The proportionality constant, the W that BMI is directly related to, and the H squared that it's inversely related to. So we are looking for K times W over H squared, which is answer choice G, just written in a different way. Obviously this is the same as K times W over H squared, and if that's not obvious to you, you need to review section 5, the fractions section. But either way, that is it for proportions and variations. So remember, most of the proportions you'll see on the SAT are of the direct variety. You will also need to do some unit conversion, so you should know this general process here, how we get from starting to desired units. You may also see an inverse proportion or variation on the test. You should know what the difference between a direct and an indirect, or, ooh, I just caught a mistake. This is not supposed to say indirect. This is supposed to say inverse. I'm going to have to go ahead and change that in my manual. That is supposed to say inverse. There is indirect proportion or variation and inverse are not equivalent to each other. The technical term is inverse. So you may want to change that in your manual if it's not already changed. And then proportion translations, which you'll see pop up every now and then, and they will be easy points if, as I have said several times, you just memorize what we talked about in this section.